Okay, this is our second introductory problem for friction. And this problem asks us, it says a rubber hockey puck has a mass of 0.2 kilograms or 200 grams. And we want to know how much force we have to apply to this hockey puck to keep it sliding at a constant velocity. Okay, so first things first, it's a force problem. Every time you have a force problem, we draw a free body diagram. Okay, so we have a surface that is ice. We have a hockey puck that is rubber. Okay, we have forces acting on our hockey puck. We have the force of gravity, which points straight down. It's sitting on the ice, and the ice is applying some reaction force to our hockey puck. We have an applied force, which is what we're trying to find. And we have the force of friction, which is something we don't know either. Okay, so first things first, when we look at this problem, we see these really important keywords. Constant velocity. So anytime you see the words constant velocity, or anytime you see the words at rest, I want you to think about translational equilibrium. I want you to think zero net force, and I want you to think there's no acceleration. Okay? If you keep that in mind, it'll treat you very, very well. So if you see the words constant velocity or at rest, you know that the object's in translational equilibrium. It has zero net forces, and it has no acceleration. It might be moving if it's moving with a constant velocity, it's just not accelerating. Okay, so let's start solving our problem. So we know that there's zero F net, which means all our forces are balanced. So the force of gravity in this case has to equal the force going in the opposite direction, the reaction force, and our force applied has to equal our force of friction. It's just the way it is, because I have no, it's in translational equilibrium. There's no net force. Okay, what's next? Okay, so in this case, we have a sliding hockey puck, which is another important thing to look for. If we see the word sliding or moving in any way, that means the object is moving. Okay, and if the object is moving, we are not talking about static friction anymore. We are now talking about dynamic friction. And we know that dynamic friction is equal to, our force of dynamic friction is equal to our coefficient of dynamic friction times our reaction force. Okay, I do a little quick substitution. So I know that, so I know my force of friction is my force of dynamic friction in this case. So I can drop this term over here into here. Okay, so my coefficient of dynamic friction times the reaction force is equal to my force applied to keep the object moving at a constant rate. I also know that, what else do I know? I know that the force of gravity, I know that the force of gravity is equal to my reaction force, and I know that my reaction force, or my force of gravity, is mass times the acceleration of gravity. So I can do one more substitution, and I can put my numbers in now. So my coefficient of dynamic friction for ice and rubber is, what is that? It is 0.2. Is my coefficient of dynamic friction for ice and rubber. So I could say 0.2 times a mass of 0.2 kilograms times acceleration of gravity, 9.8 meters per second squared. I can solve this now. So 0.2 times 0.2 times 9.8 gives me an answer of 0.4 newtons. Okay, so in order to keep the hockey puck sliding at a constant velocity, I need to apply 0.4 newtons of force to it. That's it.